Welcome to learning the Unix command line. My name is Chip Castle and I'll be your instructor. This course is intended for newcomers to the Unix operating system, which comes installed on all modern Apple computers. To be accurate, that system is called OS X, but because so many people refer to it as OS X, you might also hear me say that throughout the screencast version of this course. The goal of this course is to provide an introduction to basic Unix commands and concepts. At the end, students should possess the skills necessary to get around the system, as well as the ability to learn more about the system on their own. So here's a brief outline of the course topics. To start off, we'll cover some of the benefits of learning the Unix command line, as well as a brief overview of Unix history and philosophy, and why it's important. Since we'll be using the default terminal application that comes shipped with the Mac, it will be useful to understand how to configure it to suit our needs, especially in terms of its overall look and feel. In the Getting Help section, I'll demonstrate how to access the system manual so that you can get more information about the commands we'll be discussing, and how to get the most out of those commands. You'll learn how to navigate the directory structure, manipulate files, and have a general grasp of how they are organized on the system. I'll cover what file and directory permissions are, a couple of common ways those permissions can be modified, as well as user and group ownership. I'll also cover redirection and pipes, which in my view is one of the most fundamental features of the Unix operating system, and see how using filters can be so powerful. You'll learn how to view processes on your system, the difference between background and foreground processes, as well as how to communicate with processes and stop them using Unix signals. To get the most out of any system, you'll need to understand how to install and remove software. There are a variety of ways that this can be accomplished on the Mac, and I'll cover the more common approaches. We'll also cover various features of a shell, such as using aliases to minimize keystrokes, what environment variables are, and how you can use shell initialization files to set those variables. So that's the overview. Let's get started learning the Unix command line. Before embarking on this course, you might be asking yourself, why should I learn the Unix command line? To help you make that decision, I've put together a list of reasons why you might want to pursue learning more about Unix. You want to be a software developer or systems administrator. You're pursuing a degree that requires Unix knowledge. You want to contribute to open source software, or you simply want to understand your system better so you can fix it yourself. If any of those reasons resonate with you, then hopefully you'll find this course to be a valuable first step in becoming more proficient with the Unix operating system and its various tools and concepts. In 1969, Ken Thompson, Dennis Ritchie, and other researchers at Bell Labs started working on an operating system that would eventually be known as Unix. Since that time, many different variants of the operating system have cropped up, such as Solaris, Linux, Mac OS X, and many others. Several decades since its inception, Unix is still at the heart of the Internet and computing in general. In my view, a tool this powerful that has withstood such a rapid change in a fast-paced industry, with tools and techniques that are still essential to our everyday work, is something that needs to be learned and used regularly. Throughout the history of Unix, there have been countless contributors to its source code, associated tools, and its overall philosophy. Although I cannot cover them all here, I'd like to discuss a few of my favorites. First is Mike Gancar's The Unix Philosophy, where Mike is credited with such phrases as "small is beautiful" and "make each program do one thing well." Next up is Richard P. Gabriel's design philosophy, "worse is better," which is the idea that quality does not necessarily increase with functionality. And last, there's Eric S. Raymond's The Art of Unix Programming, which reminds us that the Unix philosophy basically comes down to applying the KISS principle. You can use these references as a starting point to learn more about the Unix history and how these ideas helped form the overall philosophy, which in my view drove much of its success. Then take what you've learned from these and other resources to help form your own philosophy and work style, as well as helping you improve your overall usage of the Unix operating system itself. Unix is an enormous topic, and the tools available are virtually limitless, but after working with it for over 20 years, I've found that a little knowledge can take you a long way. I've worked with a number of newcomers to systems administration, as well as junior and even some senior software developers who simply did not have the Unix knowledge necessary to solve certain problems. Even non-developers like front-end engineers, user interface designers, and general Mac users could greatly benefit if they had at least a basic understanding of how to get the most out of their system. With an understanding of the core principles and commands, anyone that has the interest can learn what it takes to become a Unix wizard, or at a minimum have a level of expertise and comfort with the operating system that makes their job easier. My hope is that this course will help you do just that. In this section, we'll need to select software that gives us the ability to type in shell commands. Before we even get into the various concepts and commands that Unix offers us, we need an application that gives us a command line, which is essentially an interface to a shell. This kind of software is often referred to as a terminal emulation program, or more commonly, a terminal. Throughout the history of Unix, there have been many different terminal applications made, but for the purposes of this tutorial, I'll be using the default terminal application that comes shipped with OS X, so there's nothing extra that you'll need to install to get started. With our terminal choice out of the way, let me demonstrate some of the more common ways for accessing it. If you're the kind of user that prefers using a mouse or trackpad, I would suggest that you use the Finder to access the terminal. By default, the Finder is located on the dock, which should be at the bottom of your screen. As you can see, the Finder is represented as a blue smiley face icon on the far left of the dock. To access the terminal from here, you can click the Finder, which should load a window containing a number of files and folders located under your account. As a side note, whenever you hear the term folder, remember that it is synonymous with the term directory, which is how it's more commonly referred to in Unix circles. Regardless of which term you use, a folder or directory is simply a container for other files and directories. With the window now open, I'll click on the Applications folder and then scroll down until I see the Utilities folder. I'll then double-click on the Utilities folder and scroll down until I find the terminal application. Finally, double-clicking on the icon will launch the terminal. Personally, I think that's too many steps to access the terminal, so let's look at a few other ways to quickly access it. Apart from clicking on the Finder icon located on your dock, another option for accessing the terminal is by using the Finder menu at the top of your screen. From there, you can select the Go menu and then click on the Utilities menu option. From within the Utilities folder, you can click on the terminal icon located near the bottom of the list. If you are accustomed to using keyboard shortcuts, you can alternatively access the Utilities menu by simply pressing the shortcut Shift-Command-U. The easiest thing to do now that we've found the terminal is to simply create a desktop shortcut from here. First, be sure you have the terminal selected. Then use the mouse to drag the icon over to your desktop. Now that you have created the desktop shortcut, you can simply double-click on the terminal whenever you need it. Out of all of these different options, my personal favorite for quickly accessing the terminal, or any Mac application for that matter, is by using the Spotlight feature, which can be accessed by pressing a keyboard shortcut, Command-Space. Once Spotlight is launched, just start typing the word terminal into the text field, and Spotlight will immediately start populating the list with items that match what you type. You can then select terminal from the results list and you'll see the application will be launched. One nice feature of the Mac is that we can specify applications to be automatically launched whenever we initially log into our account. To access this using Spotlight, I'll use the Command-Space shortcut that we discussed previously and type Users and Groups. Then I can select my login account and click on the Login Items tab. From there I can click on the plus sign icon, where I can find and then select the terminal application. Now, whenever my system boots up and I log into my account for the first time, I should see that the terminal application is launched automatically for me. As you can see, the default look of the terminal is fairly bare bones. So before I start using it on an unfamiliar machine, the first thing I like to do is customize it a bit to make the text more readable, as well as select the colors that suit my preference at the time. First, let's load up the terminal preferences, which can either be accessed from the menu bar, or better yet, can be accessed using a keyboard shortcut, Command, comma. The nice thing about this keyboard shortcut is that it's the same one used for preferences of most Mac applications, not just the terminal. So I would encourage you to memorize this shortcut because you'll find it often comes in handy. Once the terminal preferences are loaded, be sure the Settings tab is selected. As you can see, the Mac comes preloaded with a reasonable number of profile options to choose from. If you'd like to see how one looks, just select a profile and open the terminal. If you find one you would like to use on a more permanent basis, make it your default profile by simply clicking the default option at the bottom. For this tutorial, you're not required to change the profile on your local system. It's a completely optional step, so if you're not interested in learning how to customize the terminal, please feel free to move on to the next chapter. However, I will be making those profile adjustments for this tutorial because I think it will benefit readability, as well as the fact that I think it's a useful thing to know how to do. Because there are so many terminal profiles that are available for download, I'd prefer to select one of those instead of using the profiles that come pre-installed. Let's go ahead and do that so you can see how to import them properly. The terminal profile that I'm using at the moment is the Himisu theme. It's available on GitHub as a public repository, so let's go download it. The easiest way to handle the importing is by first downloading the zip file from GitHub and then unzipping the archive. Once that's done, you can just double-click on any file that ends with the .terminal extension. Another way of importing can be done from the Settings tab of the Terminal Preferences window. From there, simply clicking the gear icon will open a window that allows you to select a terminal theme. Now that the theme is imported, I would like to change the font to Menlo and then bump it up to 24-point type, which I think will be large enough to be easily readable for the remainder of this tutorial. Additionally, from the Text tab, you also have the ability to customize the colors as well as tune how the cursor looks. From the Window tab, you can customize the title, such as the active process name or TTY name, as well as set colors or an image to be used on the background, and also window size and scroll back. From the Shell tab, you can set parameters for when the shell starts or exits, as well as whether or not to prompt when the terminal closes. From the Keyboard tab, you can see various key mappings and edit them to suit your specific needs. Finally, from the Advanced tab, you can set your terminal's emulation mode, whether or not to use an audible or visible bell, as well as settings for character encodings. So that should cover it for this chapter on getting started using the terminal. We've covered how to easily access it, as well as how to perform basic customization. We also showed how to import a theme or profile into Terminal so that you can drastically improve the look and feel of the application to get the most out of it. That should be enough for you to easily follow through this tutorial as we explore more about the UNIX command line. In this chapter, we'll be covering various ways of getting help on a UNIX system. What's the best way to accomplish this? For starters, you could always do a Google search for specific help, but sometimes an internet connection isn't available, so you need an alternative way of looking up information. In my opinion, the most straightforward way to find help is just to use the UNIX manual that comes installed on your system. Most UNIX users refer to that manual simply as the man pages. Taking a look at the structure of a man page, you'll often find that there is a name heading, which is used to describe a command or system function, followed by a synopsis heading which describes the basic usage of that command. After that, you'll most likely see a description which should provide an expanded explanation of the command, followed by a heading for options which lists the various flags or switches that a command supports. A Unix man page will often refer to many other items. Here's a brief list of the more common ones that you'll find. Please take note of the See Also heading of any man page, as it provides references to related commands that you might find helpful. Remember that there is not a fixed structure to these documents. Software engineers from around the world contribute to these pages, and each one generally has their own preferred format. One man page can certainly differ from another, but you'll often see many of these headings as a general convention, so it's helpful to be aware of them. Man pages are not meant to cover every nook and cranny of a given command, but instead should be used as a general guide for its usage. This can be a stumbling block to Unix users, especially those who are beginners. Just keep in mind that as you become more comfortable and proficient with the operating system, you'll find the man pages to be an extremely valuable resource. So it's useful to get accustomed to using man pages in the early stages of your learning process so that you can develop good habits for the future. Let's dive into the syntax of a man page. For this example, I'm going to select another command. From the terminal, type in man followed by ls. What this says is, please give me the man page for the ls command. Looking at the man page for ls, we can see a name heading which describes how this command is used to list the directory contents. If you're not familiar with directories, just think of them as a folder or container on your system which can contain files and other directories. From the synopsis, we can see that the ls command has quite a large number of flags that are listed in bold. All of these flags are surrounded by brackets, so that tells us that they're all completely optional. After the flags, we see another pair of brackets with the word file underlined. The use of the underline means that this file is a user-specified argument. But since this file argument is displayed within brackets, we know that it is also optional. Let's see this in action. From my current directory, I can type in the ls command and see its output. Since I didn't specify any arguments, it will list the contents of the current directory by default. The detail is sparse, so let's try to find out more. Revisiting the man page for the ls command, we can review a list of available options. One popular option is a flag for listing the long format of a directory contents, which is demonstrated by issuing the following. As you can see, the result of that command shows the contents of the directory, but the output is much different than before. This time it shows the permissions of the directory or file, the amount of links or directories found within that directory, the user and group ownership of the file size, the date of the last modification of the file, and finally the name of the file or directory. Looking at the man page one last time, we see the user-specified file argument is followed by an ellipsis, which indicates additional arguments can be specified. Revisiting our example, I could demonstrate passing multiple arguments to the ls command by running the following command. The result now only shows the contents of those directories I specified as optional arguments, as opposed to showing all of the contents of the current directory as it did in the first command. Some man pages will specify options or flags separated by a vertical bar or pipe. Since the ls command doesn't have this in its man page, I'll need to show you another command to demonstrate this syntax. From the terminal, type in the man page for the pwd command. The synopsis of this man page shows that the pwd command can accept two different options as indicated by brackets, and that these options are mutually exclusive as indicated by the vertical bar. In other words, the pwd command can accept either an L or a P option, but using them both together might not have the effect that you expect. Following the man page, I see that passing the L option to the pwd command will return the logical current working directory, while passing the P option will return the physical current working directory, which means that all symbolic links will be resolved. Let's focus on the options we pass to this command and how the output might differ depending on what we pass in. As a side note, it's important to recognize that if no options are specified, the L option is assumed. Let's try this out. I'm going to change into the var directory to demonstrate. Next, I can run the print working directory command. From there, I see that the current logical working directory is returned, which is the var directory. Since passing the L option is assumed by default, this command should return the same value, which it does. Let's now pass in the P option. This time a different result is returned. It shows that the private var directory is the physical current working directory, meaning that the symbolic links have been resolved. Passing in different options returns different results, which is what one might expect. But what happens if we pass in both options at the same time? First, I'll pass in the L option, immediately followed by the P option. It returns the same directory location as if I had only passed in the P option. However, if we swap the options and called it with the P option first, we'd end up with an entirely different result. The takeaway here is that it's helpful to understand what options are available for a command and which ones won't have any effect whatsoever if they're used in combination with other options. As a side note, if you were paying very close attention, you would have noticed that I combined both options after using a dash as opposed to separating them out like so. Either syntax is correct, but I prefer to combine them since it's a shorthand way of expressing the same intent. This is true of many Unix commands, so please use it where possible, and be sure to consult the man pages if you're unsure of the options or arguments available for a command that you're using. Because there are volumes of information related to Unix commands, system calls, and other miscellaneous information, the man pages are divided into the following sections. The large majority of the commands that you'll use as a beginner can be found in Section 1, which is the General Users Commands section. Of course, as you become more proficient with the system, especially if you become a systems administrator, you'll find that Section 8 will come in handy as well. Other important sections, such as system calls and library routines, are reserved for more programming-specific information. The main reasons for wanting to become familiar with the various man page sections is not only to understand the overall structure and organization, but also so you can find additional information about the system. For example, let's revisit the man pages for the ls command. Near the very bottom of the documentation, you'll notice a heading called See Also. From here, there are a number of related commands listed, including one named symlink. If you look closely, it actually refers to it as symlink with 7 in parentheses. This means that we should review Section 7, Miscellaneous Documentation, for further information. That's the same syntax as we've used before for looking up a man page, with the exception that this time we're specifying the man page section before the command. As you can see, this man page is devoted to describing what a symlink is, as well as some history and common uses for it. Let's contrast this with the conventional way of looking up documentation for the symlink command as follows. This time the documentation is much different, as it shows programming specific details such as the header file where this command is defined for the C programming language. There is also a description of what this library call does, its possible return values, as well as common error codes that you might find important if you are using this function call while programming. The important part to remember here is that some commands or system calls can be found in multiple sections of the man page documentation, and sometimes specifying the section number is crucial to getting the exact documentation you need. Let's now turn our attention to a couple of utilities that can help you find more information about the command you'll be using on your system. The first utility is the whatis command. Let's take a closer look at it. As the man page indicates, the whatis command searches a set of database files containing short descriptions of system commands for keywords and displays the result on the standard output. Let's give that command a try. This time I'll do so by looking up the ls command. As you can see, it shows a number of results that all have ls within their command name. I can look at the corresponding descriptions and use the man pages for those commands shown to see if there is further information that would be helpful to my particular problem. The next utility I'd like to show is the apropos command. Again, let's reference the man page to find out more details. As its man page indicates, the apropos command works similar to the whatis command. However, it is a much more feature-rich command than the man page indicates, because it also searches through the man page abstracts, man page titles, and will also return results for matching only a part of a word. Let's try the apropos command using ls as an argument. As you can see, the results are much more verbose than when we used the whatis command. So that's it for the Unix man pages. As you become more experienced in your Unix knowledge, you'll find the man pages to be one of the most useful tools on the system. Before you launch that web browser and start searching the internet, please try out the man pages as well as the what is and apropos commands to help you find what you need. In the bash shell, the help utility can be useful for finding more information for some of the shell's built-in commands. By default, typing help without arguments lists those commands. For specific help on any of those commands listed, just type help followed by the shell built-in. As an example, here I'd like to get help for the export built-in function. In recent years, there's been another alternative to the Unix man pages. This system is called info, and it refers to documentation in info or TechInfo format. It is based upon GNU Emacs, which is a popular text editor among programmers. Let's give it a try. As you can see, it provides output very similar to the man pages, but navigating the system is much different than with the default system pagers such as less or more. If you're an Emacs user, you'll probably find the navigation to feel more natural. At this time, the info pages are not as widely adopted or common as the Unix man pages, but I encourage you to try them out as an alternative source of system information. That wraps up this chapter on getting help. We've looked at man page structure and style, as well as several ways to find out details about command usage. We've also reviewed a few ways to find out about other commands on your system. If you'd like to find out more information on man pages, please look up the documentation for the man pages command. Being able to work with files and directories is essential to using the Unix operating system. We'll start off with a basic overview before diving into specific commands for manipulating the file system. In Unix, as in many other operating systems, a file system is simply a collection of directories and files that are organized in a tree-like structure. The following diagram is a sample directory structure on my local system. Each directory is a folder-like structure that can contain files or other directories beneath it. At the top, we have the root directory, followed by all of the directories located immediately under it. Drilling down further, this time only showing the contents of the users directory, we see 4 other directories: shared, admin, chip, and screencast. The last directory is for the screencast user, showing that it contains a directory for desktop, downloads, library, music, and public. Here's the basic organization of a directory hierarchy for OS X. Take a moment to familiarize yourself with these directories, as each one has a specific name and purpose that helps keep related files organized on your system. To fully understand this hierarchy, you'll have to grasp what path names are and how they're used. To do this, let's get a listing of contents of the root directory using the ls command. As you can see, a number of directories that we previously described are listed here. Using the -1 option, we're able to see the data in an alternative format that displays on a single column for readability. But let's dig a little further. Let's say I wanted to view the contents of the users directory. I know it's available immediately off the root directory, so I would do this first. Notice how we've used a / character followed by the name of the directory. Looking at those results, I see that the screencast account is located beneath it. If I wanted to see the contents of that directory, I would need to use this command. Do you see a pattern here? Basically, directories are separated by a / character. By default, the output from the ls command is only 1 level deep, but I can view more files and directories within that tree structure by using the -r option, which means to recursively list everything under the directory I specify. That command resulted in an enormous amount of information being displayed to the screen, so obviously that directory contains a complex hierarchy. Let's look at another option for the ls command, which is the long format. This is one of my personal favorite flags to pass to ls because it packs a lot of information into a single option. Taking a look at the output, we can see that we have permissions listed in the first column, followed by the number of links, then the owner of the file or directory, the group it belongs to, the date and time of when it was last modified, and finally the name of the entry. Notice the first character on each line, which designates what type of file it is. To understand the different UNIX file types, let's take a look at the following table. Now let's try the same directory listing, but this time pass the -A option to be sure that it also lists all the dot directories. Underneath the User's Screencast Documents directory, we have a number of directories specified with the D character, as well as a number of regular files as indicated by the dash character. For other examples, we can look at the dev directory for various devices. Within that directory, there are a few block special files in addition to a number of character special files. In the following directory, we see examples of socket link files. And here we can see an example of a symbolic link file. What these files do isn't important at this stage, but rather that each file in UNIX has a special category or designation that it belongs to. And by using the ls command, we can determine what those values are for a given file or directory. Let's revisit the file types one last time. Before we go any further into manipulating files in this chapter, I want to cover a quick and easy way to create files. There are a number of ways to do this from the command line, but using the touch command is one of the easiest. Now let's take a look at the directory contents again. Using the long format and showing all files with the -A option, we should see the dot directories and also the drink file that we just created. It's an empty file, so there are no contents to show, but it will at least allow us to demonstrate some of the upcoming commands for manipulating files. Let's create a few more files using the touch command so that we can see how using wildcards can be so useful. The first wildcard that we'll cover is the star, which is represented by an asterisk character. It can be used to match any number of characters. So if we were to specify it like this with the drink file, the result would be any file that starts with the pattern drink. Alternatively, we could use it to match files that match any ending pattern, such as a file suffix. Here I'll create a few more files to demonstrate. Using the following pattern, it should show me any files that end with a period followed by the letters HTML. It can also combine these wildcards, as in this example. This means to list any file ending with a period followed by the letters HTM and then 0 or more of any other characters. The next wildcard I'll cover is the question mark. This character will match any single character, which can be anything. Using the following example, it says to give me a list of all files ending with a period followed by the letters HTM and then any single character. Notice how it didn't match the file 3.htm because that file name doesn't contain a single character after the HTM file suffix. To see another example, let's create two files. If I were to use the following pattern, it would list both files because it's looking for any files that start with an F followed by a single character and then end with the letter T. The last wildcard that I'll cover are the square brackets. This will match any of the characters that are enclosed within them. As an example, let's list any files that end in either the letter L or the letter G. Let's create a few more files to demonstrate further. And to expand upon that, let's list any files that start with FO and end in either an A, B, or C character. As you can see, the results listed match only the files matching the pattern we specified, not all the files that we created. We've already seen that we have directories already on our system, but what if we want to create a directory on our own? Well, that can be done using the make_dir command and then specifying the name of the directory. Let's say I want to create a projects directory. But what happens if I try that again? As you can see, the command line tells you that the directory already exists. Now that we have directories, how do we navigate between them? Well, we can use the cd command, which stands for Change Working Directory, and is one of the most common commands you'll find on Unix. Let's change into the projects directory that we just created. Then let's look at the contents of this directory. This doesn't show much, which I guess is to be expected since all we did was create an empty directory. Although they aren't immediately visible, there are two special directories that exist here. Let's dig a little bit deeper using the ls command to get a better understanding. This time let's pass the ls command the A option so we can see all of the files, and let's do that using the long format that we've used before so we can see more details. As you can see, there are two entries. The first, which is displayed as a single dot or period, is a representation for the current directory, which is the projects directory itself. The second entry is displayed as two dots or periods, and is a representation for the directory immediately above our current directory. By using the pwd command, which prints the current working directory, we can see that we're currently inside the projects directory. So the single dot represents that directory, while the double dot represents the user's screencast directory, which is directly above it in the file system hierarchy. Now let's try out these commands. This basically says change into the current working directory, which basically does nothing. However, if we use the double dot version, it changes us into the directory above, user screencasts, which is coincidentally our home directory for the username screencasts. Now let's go back to the projects directory for a moment. If I wanted to go to my home directory, I could always type it in using the full path name. However, there's a much more common way to do this, and it requires typing only a single character, which is the tilde character. If you wanted to go to another accounts directory on the system, you could pre-pin the tilde character in front of the account name, as in the case here where I'm going to the home directory for the chip account. So what happens if we change into a directory that doesn't exist? The shell provides an error, which is helpful. Another shortcut that I find helpful is using the dash to help me return to the previous directory. So let's say I change into the projects directory again, which is located under my home directory. And later I decide to change into the TMP directory, which is where the temporary files are stored. I can always return to the previous directory just by using a dash. And then let's check to see where we're located using the pwd command. As you can see, I'm back into my projects directory. Let's now see how we can view files. By doing this, we'll be able to inspect the contents of the files and have a better grasp of what happens when we move files, copy them, or manipulate them in other ways. First, I'm going to create a file called to-do with a few items in a list so that we can demonstrate these commands. And for this tutorial, I'm going to use the Nano text editor, which is very easy to use and available on most Unix systems. From within Nano, the Help menu can be found at the bottom of the screen, which shows the basic commands for operations such as opening and saving files as well as exiting the application. The keyboard shortcuts start with a control character indicated by a caret symbol, followed by another character. As an example, exiting Nano requires the Ctrl-X keystroke combination. Off camera, I created a file called to-do. Now that I've created it, how can I quickly view its contents without opening a text editor? Let's take a look at a few commands that can help you accomplish this quickly. The first command that comes to mind is cat, which is used to view the contents of a file. It can also be used to concatenate multiple files together, which is how it got its name. For now, let's just focus on using cat to display the contents of the to-do file I recently created. As you can see, it displays the contents of the file. Let's say I have a really large file and I don't want to see the entire contents fill up my screen. In that case, the cat command might be overkill. What you really need is a way to display the contents of a file one page at a time. Years ago, the first command that I'd use to page through the contents of a file would be the more command. Originally, the command only allowed for forward movement. Later, a similar command called less also provided the ability to page through the contents of a file, but also allowed for backward as well as forward movement. It follows a similar syntax to more. Just provide a file name after the command. Today, you'll find Unix users more commonly refer to the less command. In fact, on some systems, the more command is simply linked to the less command. On my system, I don't find any evidence of that linkage, but it appears that the commands are exact copies of each other. In any event, on most modern systems, you might be able to use the commands interchangeably, but just bear in mind that using less is what you'll commonly see used. Let's now move on to other ways of viewing file contents. For example, maybe I just need to see the first few lines of that file. The easiest way to do that is to use the head command. Notice that by default it only shows the first 10 lines of the file, not the entire file. Also, I can easily change the default by passing the N option and then a number. Alternatively, I can display the last 10 lines using another command called tail. The tail command also has an in option. Here I'm specifying the last 12 lines of my to-do file. However, I could have specified any number after the in option, just like I did with the head command. Now that we know how to navigate around directories, as well as list their contents, we might need to copy files around. So let's look at the basic syntax. First, we have the cp command followed by a source file and finally a destination file or directory. Let's create a test file with some contents to try this out. Now let's copy test file to another file name. And now let's get a directory listing. We can see as a result of running the cp command that test file 2 has exactly the same permissions, ownership, and size as the source file called test file. And just out of curiosity, what would happen if we copied test file over to the same file name? We get an error because test file already exists. Alternatively, we can copy files to directories. And we can see from the directory listing that the file was indeed copied there. But what happens if I were to copy a file to a non-existent directory? Let's try this out, but before doing so, let's get a listing of our top-level directory to see what does actually exist. I can see there isn't a directory named foo, so let's try copying there to see what happens. As expected, we get an error because the foo directory doesn't exist under our top-level directory. Now I'd like to create a hierarchy of files and folders for us to work with. Using the make dir command, I'll pass the p option. An additional feature of the copy command includes the ability to copy an entire directory tree. Now that I've created a docs directory, let's take a look at the contents, adding in the recursive option so that we can see the entire tree of the directory and files. Looking at the results, we can see that the docs directory contains one file, 1.txt, and one directory named work, and that the docs work directory only contains two files. So how do I copy the contents of the directory tree? Just pass the recursive option to the cp command like so. Here we're recursively copying the docs directory over to the more docs directory. So let's get a directory listing to take a look. As you can see, it contains an exact copy of all directories and files, preserving their permissions and ownership. Sometimes instead of copying files around, you simply want to move them. In Unix, the move command is similar to the copy command in that you type the command first, followed by a source file, and then finally a destination file or directory. So let's create a few files to see various ways to move them around. And then let's take a look at the contents just to verify what they contain. First, I'm going to move the file named Apple to the private temp directory. Taking a look at that directory, we can see that it indeed was moved there. Inspecting our current directory also verifies that the file wasn't simply copied, as it no longer exists there. So what would happen if I decided to move the banana file to a file that already exists, like the grape file? It would simply rename the banana file to grape, so the contents of the original grape file would be replaced with whatever the banana file contained. Listing the files, you can see that the banana file no longer exists because it was renamed to grape, and that the grape file contains the contents of the original banana file. Now that we've learned how to create files and manipulate them in a variety of ways, sometimes it's useful to do a little housekeeping and clean up our mess. Let's take a look at a few files we've already created. Then let's say I want to remove a file called fit. I simply use the remove command followed by the name of that file. Alternatively, I can provide a list of files. And we can see that those files were in fact removed. Additionally, I can provide a wildcard to remove files matching a pattern. This time it removed all files in my current directory starting with the letter F. The remove command also has the ability to remove directories. I'll create a directory with a few files just for this example. Now we can attempt to remove the directory. But as you can see, it gives us an error message. However, if I specify the recursive option like the following, you can see that the directory was indeed removed this time. Additionally, there is a command that is specific to removing directories. That command is rmdir, so let's set up a directory with some files again and try it out. Here I'm simply creating a directory called junk which contains 3 files, 1, 2, and 3. Listening to the contents of that directory, you can see that it does in fact contain those files. So if I try to remove the directory using the rmdir command, it will return an error letting me know that the directory is not empty. So let's see what happens if the directory is empty. This time around, the command will work because the directory is indeed empty. In my view, using the rmdir command isn't that useful, since the rm command or remove command can not only remove files, but also directories regardless of whether they contain files and directories themselves. So I find that I generally stick with using the remove command instead. Sometimes it's helpful to have the ability to search through files. Maybe you've been working on some markup in HTML or CSS for a website, or writing some code in a language such as Ruby or JavaScript, and you need to search for a pattern such as a CSS class name, a function or method name, or some string that you need to change. You might have many files that contain this string of characters, so manually opening these files would be too cumbersome and time-consuming to do in an effective way. In those situations, one command that would be helpful is grep. First, let me show you a few files that I've set up that contain random items within them. First, we have a to-do file that contains a few tasks that I wanted to accomplish, then a file named Apollo that contains a quote from that mission, and finally a file called collaboration, which contains a sarcastic definition of the word. So using those files, let me show you the basics of grep. First, you type the command followed by any options, then a pattern to search for, followed by a file path or list of files that should be searched. Here I'm searching for the pattern CO within the to-do file. Alternatively, I could search through all three of those files with this command. As you can see, two of the files match the pattern provided. Now let's try the same search passing the I option, which means to do a case-insensitive search. Now that you can see that all the files match. But what if I wanted to get the count of lines that match the pattern? In that case, we can just pass the C option. Let's say we wanted to just see the files that match the pattern but weren't interested in the content. In that case, we can just pass the L option. From there, we can see that only the file names are returned in the results. The grep command also has an option for returning the lines in a file that do not match a pattern. So let's revisit the contents of the Apollo file first. And let's search again to see the results. And now let's see the lines that don't match the pattern using the V option. And one of the most powerful features of grep is the ability to search recursively through directories for a specific pattern. To prove that, I'm going to create a directory structure and move a few files to it. Next, I'm going to list the contents of the temp directory recursively to see all the files that it contains. Now I'm going to change it to the temp directory. Then I'll run grep, but this time I'll do the recursive option along with the case-insensitive option. As you can see, the results include the files in the current directory and the directory below it that I just created. Keep in mind that the grep command has quite a few variations, including egrep, fgrep, zgrep, zegrep, and zfgrep, as well as other commands that provide similar functionality to grep, such as ac, and finally ag, which is known as the silver searcher. Considering the wide number of commands available for searching files, as well as the variations of regular expression engines that come along with those commands, it's difficult to learn every variation with great detail. In my own experience, I've tried to first learn the basics of the commands I need, and then later experiment with other options or commands. Take small steps and build upon your existing knowledge. To begin that process, I highly encourage you to read the man pages for grep and its counterpart commands to find the ones that work best for you. Before we wrap up this chapter, I'd like to touch on a very important command that becomes much more useful as the system grows. Over time, you can accumulate more files and need to be able to quickly find them or perform some general housekeeping, such as delete files that are simply too large or unnecessary, or possibly change permissions for a batch of files. One of the best ways on Unix to locate files is to use a command called find. The find command expects a path as its first argument so that it knows where to start its search, followed by one or more options. Let's look at a basic example. This says to find all files starting from my home directory that have a size greater than 10 megabytes. Here's another example. And this one says to find all files under the applications directory that have a name that contains any number of characters followed by a period and the letters txt. Here's another example using command execution on the result set. This command should start finding from the current directory, looking for files or directories that start with the letter D, followed by any number of characters, and then using the exec switch, which would execute the ls-l command against all files, which is specified using the pair of curly braces. The command should be ended with a semicolon, but should be escaped so that shell expansion isn't performed. Here's another example, but this time we'll specify that we only want it to search for directories, indicated by specifying D for the type switch. Since the output would be extremely verbose, I've decided to specify a max depth of 1, just so it only searches through the current directory and not any directories beneath it. To wrap up our examples using find, you can also search for all files matching a specific permission setting using the perm switch. Again, we indicated a max depth of 1 just to limit the output for this example. The find command is so powerful that it can not only search for file sizes, name patterns, types, and permissions, but also owners, groups, and many other criteria. Be sure to consult the man pages for the various options available. To fully understand how to manipulate files and directories, it is important to remember that a file system can provide various levels of access to users through a permissions-based system. In this chapter, we'll cover the basics of how to read and change permissions so that you can have a better understanding of the file system as well as how to manage who has access to the files and the directories within it. To start off, you need to be aware that users and groups are central to Unix permissions. Every account on a Unix system has a unique user. Using the whoami command, I can see what login or username that it is issuing commands. Every user belongs to at least one group. Group names are also unique. So let's take a closer look at my user account, this time using the ID command. We can also look at the output in a password file format, which gives us a lot of other useful information about a user's account. The output is colon separated. Starting from the left, we have the login name or username of the account, followed by their encrypted password, their user ID or UID, and then their group ID or GID. The next field is unused. Then we have the time when the password was changed, expiration time for the account and the user's full name, their home directory, and lastly we have their login shell. Now that we know that users and groups are central to file and directory permissions, it's important to know that this system contains 3 distinct classes for permissions, which include the following: user, group, and other. Examples of how each of these permission classes is used will be shown in the Common File Permissions section later in this chapter. As a side note, the user class is also sometimes referred to as owner of the file or directory. The other class is often referred to as everyone else. Permissions are applied to every file or directory to determine what a user or group can do with it. We can view those permissions by using the ls command that we've seen previously. The output that is returned is displayed using symbolic notation, which is one of the 2 notation types that can be used when manipulating permissions. The other notation type is called numeric notation, which I'll cover later on in the section of that same name. Symbolic notation is easily recognizable because it is the default representation shown by using the ls command. Let's start with the leftmost flag, which we've discussed already in a previous chapter. The most common settings are D for a directory, or a dash for a regular file. But this flag can also contain other settings depending on whether it's a block or character device, a symbolic link, a socket, or a named pipe. Moving on, we have a remaining 9 flags. Fortunately, these can be broken down by 3 classes mentioned previously, with the user class represented by the first 3 flags, the group class shown in the middle 3 flags, and the other class shown in the remaining flags. At this time, please familiarize yourself with the following flags representing symbolic notation. The command responsible for changing file modes or access control lists is the change mode command, which I usually pronounce as chmod. In the examples that follow, we're going to start out using symbolic notation with this command, so let's look first at what each of these symbols represents. For specifying the permission class, we have the following symbols. A U is for a user, G for group, O for other, and A for all permission classes. For specifying the operation to perform, we have these symbols. A plus sign for adding permissions, a minus sign for removing them, and an equal sign for setting them explicitly. And finally, the symbols for the permissions themselves are an R for the read flag, a W for the write flag, and an X is the execute flag for a file, while for a directory it allows you to search through it. Taking a look at a file called hello, I can see that it currently has an echo statement within it. I'll remove the read permission for the user class of the file and verify that those permissions have been changed properly. As you can see, the read permission has been removed from the user class. So let's try to take a look at the contents of this file. Attempting to view the contents of the file produces an error, which is expected because I don't have read permissions on it. I'll then add back the read permission and verify that I can view the file again. In both of these examples, I followed a format of specifying the symbol for the permission class, followed by an operation to be performed, and finally the permissions themselves, such as the read permission. Using the same file, I'll now remove the write permission for the user class. Since I no longer have write permissions, attempting to write to a file should produce an error. I can add the write permission back and attempt to write the file again. Viewing the file one last time shows that it is now different because it was writable by the owner. In this example, I have a file that will echo a string. Attempting to execute the file should produce an error. This is because the owner doesn't have execute permissions. So let's add those permissions back. And then try to execute the file. This time it echoed the string, which is due to it having the proper permissions. In this example, I'm going to create a directory which contains a couple of empty files. I'm now going to remove the read permission for the user class from this directory. Attempting to list the files in that directory should cause an error because I no longer have read permissions. However, because I have execute permissions for the directory, I can use the cd command to change into it. However, I still cannot list or read the contents of the directory. Changing the permissions back to being readable for the owner of the directory, I can now list the contents. In this example, we'll first view the contents of the directory and then remove the write permission for the owner of it. And we can see that the permissions were applied properly. Let's attempt to write to the directory by adding another file. This produces an error, and we can verify that the file was not added. Let's add the right permission for the owner and then attempt to add the file again. This time the file was added properly to the directory because the owner had right permissions to do so. In this example, I will remove the execute permissions for the owner of the directory. Now that they're removed, we can try to list the contents of the directory again. However, we received an error message because even though the owner had read permissions, the ls command could not change into the directory because there were no execute permissions set for the owner. Looking at symbolic notation a bit closer, we can pass much more complex permission combinations provided we follow the proper syntax. Let's revisit the permissions for the hello file. And this time I want to add write permission for the owner of the file, but I want to remove that permission for both the group and other classes. This can be done by comma delimiting the permission classes. Let's verify how the permissions were changed. Now let's set all the classes to have no permissions whatsoever. We can see that the permissions were indeed removed, so let's add some back. But this time we can combine the group and other classes, since we want to add read and execute permissions for both. And then we can verify that those permissions were changed properly. If a file is already executable, adding the uppercase X flag to the permissions makes it executable by all permission classes. First, we'll reset a file to have no permissions. Next, we'll add an execute permission for the group. And finally, we'll add read and write permissions for the owner, but this time we'll specify the uppercase X flag as well. Since the file originally contained an execute permission for the group, it should now have all permission classes set to executable. However, it only has an effect when used in the additive case. Using it to remove the permission has no effect whatsoever. To see the effect of the X flag on a directory, I'll create one first. Next, I'll remove the permissions for it and then verify that they were changed. And finally, I'll apply the uppercase X flag in the additive mode and verify that all classes are now executable. When not used in the additive mode, the X flag is ignored. The setUID concept, which is a shorthand way of saying set user ID upon execution, is a flag used to determine what user a file will be run as upon execution. This idea will make more sense when we cover Unix processes later on, but for now let's just focus on how we can identify this setting and change it to suit our needs. I'll first reset the hello file to have no permissions. Next, I'll add the setUID bit for the owner. We see the flag is represented by an uppercase S because it's set for the file owner, but when we add execute permissions, the flag is changed to a lowercase s. Removing the setUID flag from the owner will uncover that the file now only has execute permissions for the owner. The setGID concept, which is a shorthand way of saying set group ID upon execution, is a flag used to determine what group a file will be run as upon execution. First, we'll reset the file to have no permissions and then add the setGID permission. We see the flag is represented by an uppercase S because it's set for the file group, but when we add an execute permission, the flag is changed to a lowercase s. Removing the setGID flag from the group will uncover that the file now only has execute permissions for the group. The sticky bit is a technique that is commonly used on shared directories or directories containing temporary files, such as the private temp directory on the Mac. This means that the directory itself is append only, meaning that files can only be added, not deleted. Let's take a look at a few examples of how the sticky bit is used in practice. To be clear, files actually can be deleted when using the sticky bit, provided that the user has write permission for the directory and if the file is being deleted either by its owner or by a superuser. To prove this, I'll create a file and check that I have write permissions. Now I'll try to remove the file, which should return without error. In this example, we can see a file under private temp directory which is not owned by the screencast account. If we attempt to remove that file, it should result in an error since the directory has the sticky bit set. In this example, we'll remove the execute permission from the other class. Keep in mind that this command had to be run using sudo privileges. Without the execute permissions, the sticky bit is set, but it is indicated with an uppercase T. Adding the execute permission back, we can now see that the sticky bit is reset to a lowercase t. Revisiting the permissions for the library directory for the screencast user, you might have noticed something unusual. If you're looking closely, you'll notice a new character in the far right position, which is an @ sign. So what does this represent? It means that the directory has extended attributes. These extended attributes can be displayed using some special options of ls. The first option is the long format that we've used numerous times before. It's followed by the @ symbol flag that displays the extended attributes. The D flag displays the results without showing the contents of the directory recursively. Here we can see the extended attributes. Alternatively, the extended attributes can be viewed with the xadder command, which shows the same information as before, plus some additional details displayed in hexadecimal. Now that we've covered the basics of the chmod command using symbolic notation, it's time to look at an alternative format for manipulating file and directory permissions. That alternative is called numeric notation, and it provides the ability to change permissions in a much less verbose manner than symbolic notation. So let's revisit an example of symbolic notation. This explicitly says that the user class should be set to read, write, and execute permissions, and the group and other classes should be set to only read and execute permissions. Using numeric notation, this can be done just as easily like this. To understand it fully, we need to provide a brief explanation of the binary number system. That numbering system is base 2, which basically means that every number is a power of 2, and also that we only have two choices, 0 and 1. Let's look at an example. What I'd like to do is convert a number 6 into binary. So let's take a look at the powers of 2. Starting from the right, we have 2 to the 0th power, which is 1. This is true in any numbering system. Any number to the 0th power is always 1. Moving one place to the left, we have 2 to the 1st power, which is basically itself, or 2. Moving to the left again, we have 2 to the 2nd power, which is essentially 2 times 2, or 4. So what we need to ask ourselves is, how many 4s does it take to add up to the number 6? It only takes 1, so let's set that column to 1. If we subtract 4 from 6, we have only 2 left. Moving right, we can look at the next column and ask, how many 2s can add up to the 2 we have remaining? The answer is 1, so we set that column as well. Then we subtract 2 from 2, which leaves us with 0. Since there's none left, we don't set the remaining position. If we look at it from the permissions perspective, 6 is the same as having the read and write bits set. So now that we've shown how to convert decimal to binary, let's try it the other way around. In this example, I'd like to know how we represent the binary number 101 in decimal. If we revisit our powers of 2 table, we can see 2 to the 2nd power, which is 4, is set. Moving to the right, we see 2 to the 1st power, which is 2, isn't set. And finally, 2 to the 0th power is also set, which basically means we're adding 4 plus 0 plus 1 to equal 5. If we look at it from a permissions class perspective, we see that 101 in binary basically shows that the read and execute bits are set for that permission class. Let's revisit our temp directory to drive these examples home. Looking at the collaboration file, let's focus on each of the permission classes one at a time. First, we have the user class, which is on the far left. We see that we have the read and the write bits set. Adding those numbers up would mean we would add 4 plus 2 plus 0, meaning that it's 6 for the user class. Moving on to the group class, we see that we have only the read permission set, which is basically represented as a 4. The other bits aren't set, so basically we're adding 4 plus 0 plus 0, equaling 4. The same is true for the other class. So writing this out in numeric notation would basically be like this. First, I'll reset the permissions to nothing. Now I'll add back the permissions, but this time I'll use numeric notation. As you can see, the numeric notation is a much simpler way of specifying permissions. Let's now turn our attention to the junk directory which we created previously. Again, we'll focus on each permission class individually. Starting from the left, the user class has the read, write, and execute permissions set. Basically, this means that we would add 4 plus 2 plus 1 equaling 7. For the group class, we have only the read and execute permissions set, which means we'd set the 4 plus 0, since the write permission is not set, plus 1 for the execute permission. So basically 4 plus 0 plus 1, which is 5. And the same is true for the remaining other class. I'll now reset the permissions to the junk directory so that we can see this in numeric notation. We've already covered the basics of setting permissions, but there are still a few special flags that need to be addressed. Those are the setUID, setGID, and the sticky bit, which were covered previously in the section on symbolic notation. These flags will occupy another bit position to the left of the normal permission flags. The setUID flag is assigned to the user class, which has a value of 4. This makes sense because its purpose is to set a flag for the user's process ID. Moving to the right, we see that the setGID flag is assigned to the group class, which has a value of 2. This also makes sense because its purpose is to set the flag for the group's process ID. Lastly, we see on the far right that the sticky bit flag is assigned to the other class, which has a value of 1. This makes sense because its purpose is to set a flag for the directory, which should be applied to everyone. Let's try an example with a file called myfile that has no permissions set. Applying symbolic notation where we have read, write, execute, and setUID set for the user class, and then read and execute flags set for the group and other classes, it would look like this. However, that's far too verbose, so let's try it using numeric notation. I'm going to reset the flags first so that we can start with a clean state. Using numerical notation, we can simply do this. As you can see, the setUID bit is set on the user class. Now let's look at how to apply the setGID flag. Again, let's clear out the permissions first. Now we'll apply the permissions using the verbose symbolic notation. That works fine, but I'd rather use numerical notation because it's easier and shorter if you understand the rules. I'll clear out the permissions again. And this time I'll apply the setGID flag using numerical notation. And for our last example, let's see how we can apply the sticky bit setting. Since this special flag doesn't make sense on a file, I'll be using my public directory for my account. Again, let's clear out the permissions. We can see that it has no permissions, so let's set them using symbolic notation. Again, we have read and execute permissions on all classes, and write permission for the user, but this time we're also setting the sticky bit for the directory, as shown with T notation. Now let's clear out the settings again, and try it with numeric notation. Again, we have the same result as before, but this time it was accomplished in a much simpler fashion using numerical notation. One of the most important features of a Unix operating system is its ability to manage streams of data and redirect it to an appropriate destination. Having the ability to take the output of one command and feed it as the input to another command is one of the hallmarks of Unix. It's part of what makes the operating system so remarkably powerful and allows programmers and system administrators alike to build more complex applications by chaining together many smaller, more focused utilities. It's one of the main reasons that they are able to write programs that do one thing and do it well. In this section, we'll uncover the various ways that you can use this feature of Unix to capture, redirect, and filter data. The way Unix manages streams of data is by using file descriptors, which are essentially integers that identify open files. Every Unix operating system has access to at least 3 common file descriptors: standard input, standard output, and standard error. Here's an overview of those file descriptors and their locations on the system. Standard input is data that is read into a program. A common example of standard input is reading data that a user types in from a keyboard. Of course, standard input can also be accepted from commands and utilities, as we'll see in a moment. Standard output is data that is written from a program. For example, when a command writes data to the screen or terminal, that is considered to be standard output. Of course, that data doesn't have to be written to the screen, as it can also be redirected to other programs. Standard error is basically the errors that a program outputs, such as if you pass the wrong arguments to a command, it will issue a warning or error that is written to standard error, which in many cases is the screen or terminal. To fully grasp these concepts, let's look at the various ways that we can use the standard data streams. First, I'm going to use the cat command and redirect its standard output to a file called fruits. As you can see, I'm using the greater than symbol to redirect the data. To allow this to sink in a bit, it might help you to think of the greater than symbol as an arrow that shows what direction the data will flow. I can then type in as much data as I want, but I'll need to type Ctrl-D when I'm done to trigger the file to be written. Now I can display the contents of the file using cat again. Let's now send the standard output of one command to a file. I'm going to revisit a command that we've used previously for displaying some data from this file. That command is head, which normally displays the first 10 lines of a file. But you can also pass the N option to specify how many lines you'd like to show. In this case, I just want the first line of the file to be shown. As you can see, it wrote the line containing apple to the screen. Now let's redirect that output to a file using our redirection operator. Notice how this time nothing was written to the screen? That's because the standard output was redirected to the fruits2 file instead of the screen, which is the default location. Let's review the newly created file. As you can see, the output from head was indeed written there. In this example, I'm going to create a couple of files quickly by echoing a string and redirecting the standard output to those new files. So let's review those files. Since the cat command's specialty is to concatenate files, it can accept multiple file arguments. I'm going to pass those new files to it and redirect its standard output to the fruits5 file. Using cat to display its contents, we can see that all the content from those three files has been written to the new file. One point that I'd like to stress about this type of redirection is that it not only can create new files, but it will also completely overwrite the file if it already exists. Let's take a look at an example. First, I'm going to copy an existing file to another file called fruit6 and take a look at its contents. Then I'm going to use the greater than symbol to redirect the standard output like we've seen before and enter some data. I'll type Control D to finish entering the data so that it will write to the fruit6 file. However, since the file already existed, it should simply override it with the new contents. Let's take a look to be sure. When using this type of redirection, use care and be sure you're okay with overwriting the file if it does already exist. Let's say that you don't want to overwrite a file, but instead simply want to append the standard output to the end of a file. In that case, you can just use the append redirection operator, which is representing using two greater than symbols. Let's look at an example to see this in practice. First, we'll display the contents of the fruits file. Then we'll follow an example similar to what we tried before with the cat command, but this time we'll use the append redirection operator. I'll type in some data, then just like before, I'll type Control D when I'm done. Let's now take a look at the file. This time, instead of overwriting the file, the data was simply appended to the fruits file. As another example, we can redirect standard output using the append operator, but this time do so using multiple files. Let's revisit the contents of a few of the fruit files. And then we can take the concatenated contents of these files in the order that they're listed and redirect it to the fruits4 file, this time appending the data to what is already there. And then we can review the contents of the destination file. We can see that the data from the other files was indeed appended to fruits4. As a side note, the append operator also works on files that don't exist. Again, we can concatenate a couple of files to a file called SUMFile, and it will be created with the contents of those files passed as arguments to the cat command. Here we'd like to shift our attention to redirecting standard input. This can be done with the operator that looks like a less than symbol. In this example, I'm going to send an email to myself, but have the contents of the fruits file sent to the command by redirecting standard input. This is much easier than copying and pasting the contents of a file into the body of an email message, so it's a bit of a time saver. Additionally, you can take the contents of a file and use it as standard input for other commands, like cat. Sometimes it's useful to redirect standard input and standard output on the same command. Let's revisit the contents of our fruits file. Let's say I wanted to sort this file, but I also wanted to save the contents to a separate file altogether. This can easily be done using both redirection operators. What this does is first send the contents of the fruits file to the sort command, which is its standard input. Then it sorts the file accordingly and sends its standard output to the fruits.sorted file. Take note that the output was not displayed to the terminal. Instead, the results can be found inside the new file. As you can see, the results were sorted alphabetically, just as we specified on the command line. As we've discussed earlier, standard output and standard error are by default in separate locations. Let's use an example to help clarify this concept. I'm going to get a file listing of two files, except that one of them doesn't exist. Here we see an error for the non-existent vegetables file, as well as file details for the existing fruits file. This seems normal, but there's something going on behind the scenes that might not be immediately apparent. Watch as I try the same example and then redirect the standard output of this command to a file called output.txt. This time we only see the error. This is standard error and is to be expected because we did not redirect it. However, we did redirect standard output, so we should see the results from the ls command within that file. Let's say that we'd like standard output and standard error to be sent to the same file. Here's how it's done. Taking a look at the output.txt file again, we see that indeed the standard error and the standard output were redirected there. Using the ampersand with a greater than symbol is just one of the ways to accomplish this type of redirection. As a side note, be sure to type the ampersand immediately followed by the greater than symbol, with no white space in between. There's another way to follow this technique, so let's first clean up our output file. Now we can issue the alternative format, although it is a bit more verbose. So what does this do? It first redirects standard output to the output.txt file. Notice the special notation that's being used here. In this case, we're indicating that file descriptor 2, which is standard error, should be redirected to file descriptor 1, which is standard output. And taking a look at the file again, we see that this accomplished the same result as before. Again, please bear in mind the proper syntax does not allow for spaces. Additionally, notice that the following example means something completely different. This says to take the standard error and redirect it to a file named 1, not file descriptor 1, which is the standard output. Sometimes it would be nice to redirect both standard output and standard error, but we prefer to have the results sent to separate locations. Let's try an example. The first part of the ls command says to send the standard output to the output.txt file. The next part is using the special syntax, to and then a greater than symbol, which says to redirect standard error to errors.txt. Now let's look at the output file. We can see that it only shows the results from ls. And now let's look at the errors.txt file. Here we see that it only shows the error, which is exactly what we intended. Let's say I have a program that generates an error and I'm not interested in seeing it. I can send that error to a place commonly referred to as a bit bucket, which is dev null. If my program were to do something like check for a process ID, I could do something like this. Since that file exists, it displays the contents to my terminal. However, let's try the same example with a file that does not exist. This shows an error, of course, but if I don't want to see the output, I'll need to redirect standard error somewhere. This says to display the contents of the file to the terminal, but if it runs into any errors, to just send them to the null device. Basically, it just discards the error. Let's say I have a program that generates an error and I'm not interested in seeing it. I can send that error to a place commonly referred to as a bit bucket, which is dev null. If my program were to do something like check for a process ID, I could do something like this. Since that file exists, it displays the contents to my terminal. However, let's try the same example with a file that does not exist. This shows an error, of course, but if I don't want to see the output, I'll need to redirect standard error somewhere. This says to display the contents of the file to the terminal, but if it runs into any errors, to just send them to the null device. Basically, it just discards the error. Let's say you want to test out a command using some sample text, but want to do so without opening a text editor. Basically, what you need is a temporary document. In UNIX speak, this is more commonly referred to as a here document. Let's create one with the cat command to demonstrate the idea. After typing cat, I'll use two less than symbols, immediately followed by a string of uppercase characters. In this example, I used EOF, but I could have used any string of uppercase characters as a terminator for the input stream. This tells cat to allow me to type in data until it finds that terminator at the beginning of a line. I'll then type in some text followed by that EOF terminator. As you can see, it maintains the formatting, expanded the shell environment variable, and ran the whoami command. In this section, we'll cover how to use UNIX pipes, which in my opinion is one of the most important and powerful facets of the operating system. The concept of pipes is quite simple. The output of one command is sent as the input to another command. That use of pipes is represented by a vertical bar character. Let's revisit our here document example from the previous section. I'll use the cat command to create the document, but at the end of the line I'll use a pipe symbol to indicate that the output of this command should be fed as input to the sort command. As you can see, the contents of the here document were sorted. Let's take a look at another example. I'll issue an ls command to see the contents of the current directory. That's way more output than I'd really care to see. What if I wanted to pare down this output and only show the files that contain the string fruit? I could do that simply by using a pipe. Here I'm going to pass the output of the ls command to a separate command where I grep for the string containing fruit. The result of that command only showed lines matching the pattern we specified. Take a moment and think about this idea. It is extremely powerful as it allows you to chain together multiple smaller commands and utilities, with each command being used to filter the previous command's output. In this example, I'll show a more practical use of pipes that has been very useful in my own workflow. I need to credit Ben Orenstein for the original idea though. Since I first heard of it, I've posted this tip on my free Unix newsletter at unix.chipcastle.com and received a really positive response. Based on that feedback, I've come up with a variation of this tip, which I'll show here. So what I'd like to do is find out the top 10 Unix commands that I currently use. Having this information is valuable because I can then create short aliases for these commands. Thus I can speed up my workflow because I'll type much fewer keystrokes. It might not sound like a big improvement at first, but if you type certain commands dozens or hundreds of times a day, the time savings can really add up over the long term, not to mention the reduced wear and tear on your fingers. To start off, we'll issue a history command to see everything that we've typed into the shell. we really aren't interested in the number associated to the left of the command's output. So I'm going to pipe the results of history to the cut command, which according to the Unix man pages is used to cut out sections of each line of a file. Here we instruct the cut command to remove only the first 8 characters of the output using the C flag. Now we just see the command itself returned in the results, so we're making progress. Now all I'm interested in is the command itself, not any options, flags, or arguments, so I'll need to use cut again to filter the data a little bit more. Here we see the D flag specifies that I should use a single space as the field delimiter so that it knows where to divide the data. The F flag instructs cut to return only the first field of data which is split on a space. Next, we simply sort the output alphabetically. Since there are a lot of commands that we use over and over, our output has a lot of duplicates. We can filter those sorted results using the unique command, but we must include the C option to precede each output line with a count of the number of times the line occurred in the output. To round out the most frequently used commands, we need to sort the output numerically to the command counts provided by unique, and to be sure to do so in reverse order since we're interested in the most frequently occurring commands first. Lastly, we use the head command to show the top 10 shell commands. Of course, you can always vary this a bit if you're interested in more or less commands than 10 by simply specifying the N option for head. This example is fairly straightforward and only touches on the tip of the iceberg when it comes to the true power of using pipes. One of the central ideas of Unix is to create small programs that do one thing and do it well. By using pipes, it allows us to do just that and chain together a wide array of commands to build more complex, sophisticated applications while doing so in a flexible manner. This concept also encourages old and new Unix users alike to always learn new commands. The more commands you have in your tool belt, the more options you have at your disposal when building software or maintaining a system. As a software developer, I've always felt that one of the most important things I could do is to reuse software that has already been written. By doing so, I save myself time designing, writing, testing, and debugging. It also allows me to focus on what I really want to accomplish. To wrap up this chapter, I wanted to show you a technique that combines the idea of output redirection with the functionality of Unix pipes. Let's say you're interested in how much free disk space you have on your system. That's easy enough using the df command. Passing the H option returns human readable output of the disk usage stats. But what if I also want to save those results to a file? That would be easy to do as well just by redirecting standard output to a file. That works fine, except that I don't want to type 2 separate commands. In fact, for some examples, it might not be feasible to run the commands separately because the output might differ. What you need instead is the ability to capture the output, send it to standard output, as in the terminal, and also save it to a separate file. Well, there's a command to help you do just that. That's the T command. According to the Unix man pages on OS X, the T utility copies from standard input to standard output, making a copy in 0 or more files. Let's try out our example again, but this time using T. Now let's take a look at the contents of that output file, just to be sure that the disk information was written there, in addition to what we saw on standard output. The output is identical to what we saw when we ran the original command, which is exactly the result we want. So next time you need to see standard output and also copy it to a file, remember that the T command is a great option. To start off this section, let's first think about the definition of a process. A process is an instance of a computer program that is being executed. Examples of this include any time you run a shell command such as ls, cd, or many other built-in commands, or when you launch an application from the OS X Finder. To see evidence of this, we have a couple of commands that are especially helpful in viewing running processes. The first command is ps, which shows a process status. By default, this command shows one process per line, with the format of each line being represented by the process ID, followed by the controlling terminal of the process, the CPU time, and the command that the process represents. A popular option for the ps command is to use the F flag, which shows a slightly different output. It's important to note that this format shows the user ID that owns the process, as well as the parent process ID and the starting time for the process. But let's say that neither the default output of the ps command nor the F flag is suitable for your needs. In addition to checking the man pages for a wide array of other flags to use, you can also set up a customized output using the O flag. In the following example, I'd like the ps command to simply give me the user that owns the process, followed by the process ID, also known as the PID, the status or state of the process, and finally the command that the process represents. What's interesting to note here is that the status column can tell us a number of things. First, I have several processes running the bash shell that have the S status, which means that these processes are sleeping. There's also another process with a plus sign. This indicates that it's in the foreground of the controlling terminal. So far, we've only looked at a list of processes that are owned by the user we're logged in as, which is the screencast user. If we need to look at processes of other users on the system, we'd need to pass another flag to the ps command. Using the A flag will do just that. As you can see, there are a number of other processes that I'm running on another account. These include the applications Zeus and also TMUX. Using the ps command is a useful tool for getting the list of processes on your system and has a variety of flags that can be combined to slice and dice the information that's displayed. However, ps can only provide information about processes at the very moment in which the command is executed. In other words, it is merely a snapshot of the state of the processes at a given time. To have more up-to-date data, we'll need to use another command that provides process information in real time. The top command periodically displays a sorted list of system processes. Let's take a look at top running on our system. The first few lines of output from the top command show a summary of statistics for your machine, including how many total processes on the system, how many that are running, the system load average, CPU usage, memory consumption, and other valuable info. Further down, we see that each line of output displays a process ID, the command associated with that process ID, and a number of other memory and disk-related details for the process. The top command can be an important tool for finding which processes on a system are creating a resource bottleneck, but doing so can be difficult at times when expecting the default output. To more effectively use top, it's helpful to sort the output by a different column, such as CPU or memory usage. Let's find out how to do that by using the help screen. To access the help screen when using top, just type a question mark. Taking a look at the help menu, you'll see that you can sort processes based on a specific column of output, as well as send signals to a process, including terminating a process and many other things that we'll cover in a moment. Let's say my server is sluggish, and I want to see if there's a specific process that's either maxing out the CPU cycles or simply being a memory pig. I can review that by sorting the output, so I'll type a question mark to load the help screen. Once I'm there, I can see that to sort by CPU, I'll need to type an O followed by the key name I'd like to sort by. So first I'll press the Enter key to return the process list. Then I'll press an O to sort by the key. Then a prompt is displayed which shows me that currently the processes are being sorted by the PID. I'll type CPU, and now I can see that the output is sorted by that key name. Currently, top is updating its output in near real time, basically 1-second intervals. If I wanted to change the updates to be less frequent, I can easily do that by typing the S key, which will display a prompt asking me to enter a number. I'll type 5 and press Enter. Now we can see that the output is being updated every 5 seconds. We can also send signals to processes listed from top, such as sigterm or term for short, which will send a signal to the specified process requesting that it terminate immediately. In this case, I'm going to send a term signal to a process by typing an uppercase S. Following the prompts, I can type in the signal name such as HUP for hang up, kill for kill, or term for terminate, among others. In this case, the term signal is the default, so I'll just press the Enter key. Now top is asking for a process ID, or PID. So I'll type one in and press the Enter key, at which time the term signal will be sent to that PID that I specified. If all goes well, you should see that process be terminated and it should no longer show up in the top output. Keep in mind that top can also have options specified upon the command line. So if I wanted to display the process list sorted by CPU usage, but update that output every 5 seconds instead of using the default, I'd use the following command. The S option is a flag used for the update interval in seconds, and the O flag specifies the primary key name with which to sort upon. Now that we've looked at how to view these processes using PS and top, it's time to move on to how these processes are created. One of the best ways to demonstrate this is to run programs directly from the command line. Most of the commands and utilities we've worked with so far in this tutorial have been run as foreground processes. This isn't easy to verify because most of the commands run so quickly. The processes are spawned and die almost instantly, as when we run commands such as cd, ls, and many others. However, the idea of foreground processes becomes more apparent and important when we have a long-running process. Revisiting the find command from a previous chapter, let's search for all files under the root directory with a name containing the string .plist. But what happens if you realize that the command you just entered isn't exactly what you wanted? One option would be to wait for that process to finish and then type in what you really needed. However, this would cause you an unnecessary delay, and for some processes, it might take much longer than the find command just entered. Instead, it would be really nice if there was an easy way to terminate a process, so let's do that. Whenever you have a command that you'd like to terminate, you can do this by typing Control-C. After typing that keystroke combination, you can see it shows up on the screen and the process has indeed been terminated. This is a really common technique, so be sure to remember it since you'll probably use it often. As an alternative to terminating a process, it's sometimes nice to allow the process to keep running, but just suspend it temporarily. This is easily done by typing Control-Z. I'm going to run that find command again so that you can see how to suspend it. In the next to the last line of output, you can see the Control-Z character, followed by another line which shows the process was stopped but not terminated. For us to better grasp the concept of foreground and background processes, we need a way to inspect and manage them. The jobs command is an excellent way to do that, so let's use the help utility for this built-in shell command. Let's now look at the jobs we have running on our system. We can see that the output shows the job spec, followed by a process status that indicates this job is currently stopped, and finally the full command is shown that this job represents. Alternatively, if in addition to the normal job's output, you'd like to see the process IDs associated with each job you're running, just pass the L option. If you're interested in only the process IDs, just pass the P option. Let's start over by running the find command, except this time let's redirect standard output and standard error to a file named plist.out. We're also going to run this command in the background, which can be done by appending our command with an ampersand symbol. Notice the job spec in square brackets, and also the process ID immediately next to that for that command. Let's say that you run a command and forget to type the ampersand symbol to run the program as a background process. The good news is that there is an alternative approach that can be used. The BG command is a shell built-in that can take a foreground process and send it to the background. Let's take a look at the help for this command first. So let's give this a try. We'll run that find command again and then suspend it using the Control-Z trick we learned earlier. Notice how this time we're not running the process in the background. Taking a look at the output, we can see the job spec was reported within square brackets when the process was suspended. So let's use that with BG to bring it to the background. Now let's take a brief look at the process again using the jobs command. And we can see that it's now running again. You can continue to do work on the command line, and once the process has completed, you'll see the status sent to standard output, indicating that it has indeed finished. To complement the ability to send processes to the background, we also have the ability to bring processes to the foreground using the FG shell built-in. Let's view the help documentation for this command to get more details. So let's take a look at an example of this command. I'll revisit the find command we used before, but this time I won't redirect standard output or standard error, just so you can see what's happening more clearly. First, I'll run the command and immediately suspend it using Ctrl-Z. Let's use the FG command to bring it to the foreground using the job spec. As you can see, the program runs in the controlling terminal in the foreground, sending standard output and standard error there for us to view. Although that's a good trick to know, I think this approach really shines in my day-to-day workflow when I'm writing code or working on describing a technical tip. I usually work in Vim, so let's take a quick look at how this would work. First, I would open Vim and do some work and then save it. Occasionally, I might prefer to drop out to the shell to run a command, but I don't want to go through the hassle of quitting Vim, especially when I might have several files open at the same time. It would be much easier if I could just suspend my Vim session to enter a shell command and then quickly return. We've already seen how to suspend a process using Ctrl-Z, and also how to bring a process to the foreground using FG. So let's try it out. I'll open the plist file that we created earlier. Then, while within Vim, if I decide to drop out to a shell, I can just type Ctrl-Z and I'll see that the process has been suspended. Then I can do whatever I need, such as change a file permission, look at my code repository status in Git, or run other commands. When I'm ready to return to my suspended session, all I need to do is issue the FG command. As you can see, I'm back within Vim and can continue my work there. Having all of these processes is great, but sometimes you need a way to destroy a process. Maybe you typed the wrong command, or there's a process that is eating a huge amount of memory or consuming too many CPU cycles. Regardless of the scenario, you need to prevent the process from continuing. This can be done using the kill command. The kill command is really just a facility for sending signals to a process. Using the L option, we can view a list of all signals that can be sent. To send a signal to a process, we use the kill command, followed by an optional signal, and finally the process ID or PID that we'd like to communicate with. By default, the term signal is sent to the process ID if one isn't specified. So let's run that trusty find command again and immediately terminate it using Control-Z. Now we can use PS to view the process for the current user. As you can see, the find command has a process ID of 25517. Let's terminate it with the kill command and its process ID. A little later, we'll receive the response that the process was in fact terminated, which is exactly what we wanted. As an alternative, we can pass the job spec instead of the process ID to kill the process. I'll run the find command again and immediately suspend it using Control-Z. This time we'll skip using PS to view the running processes because the output from the suspending process indicates the job spec of 1. So we can terminate it by passing that number to the kill command instead. As a side note, you always want to prepend the job spec with a %sign. I'll now run the process status again. Now we can see that the process has in fact been terminated. But what if we need to send a signal other than term? For example, it's quite common for me to send the kill signal to terminate a process, which is a non-ignorable signal. Let's do that. So we'll run the find command again and issue Control-Z. Now we can send a kill signal, which can be done using the signal names, such as the following. This can also be abbreviated, removing the sig portion of the name. We can also replace the process ID with the job spec if we want. Please notice that the dash that prepends the signal name or number is important. If you leave it off, you'll get an error. Returning to our example, because sending a kill signal is so common, it's easier to pass the signal for kill, which is a number 9. Because I've used the kill signal so many times, remembering that it is a 9 is easy. However, most of the other signals I have not committed to memory. So referring to the signal list is sometimes necessary. Let's revisit that list one more time as a refresher. In this section, we're going to install a software package using a utility called curl. The curl utility essentially allows you to transfer a file from a specified URL on the internet to your local machine. What I'd like to do is download a great application from 37 Signals called PAL, which is a rack-based web server for the Mac. According to the installation instructions, We'll use curl to fetch a file and then pipe the downloaded data to the shell, which will then run the file as if it were a shell script already on our file system. Before blindly doing something like that, I would advise you to visit the site first with your web browser or simply download the file with curl to inspect its contents. Since I've run this script many times before and know it comes from a trusted source, I'm comfortable with running the installation command provided on the site. It should provide feedback as it continues through the installation process. What's great about this script's installation is that it provides a link to the documentation as well as instructions for uninstalling the application. As you can see, installing software using curl is usually straightforward, but it's not the most common way. We'll need to look at other ways of managing software in our system if we're going to continue customizing it. Since I've started using Brew, I've run into fewer problems with software package management on my Mac. For most packages, I've found that it just works, so I've been quite happy with it. Before I cover the basics of using Brew, I would like to encourage anyone following this tutorial to refer to the website for the most up-to-date documentation on how to use it effectively, as the commands that follow could potentially change in the future. Alternatively, you can use the help provided by Brew or refer to its man page. At the time of this writing, the installation of Brew requires the following command. Since I already have it installed on my machine, I'll be skipping this step, but please feel free to pause for a moment and install it on your local machine if you want to follow along. First, I'd like to be sure that I've got the latest version of the system, so I'll perform an update of it. Please note that I'm logged in as the chip account, because that's the account that has write permissions for the Brew installation directories. And we can see that it proceeds with updating the utility. Now that I've upgraded to the latest version, I'd like to see what packages on my system have newer versions available for upgrade. So I'll do a check using the outdated argument. Your system will certainly vary, but mine responded with quite a number of packages that need upgrading. Let's say in this case I wanted to upgrade ACK, which is a great alternative to grep for quickly searching through files. This is how I would perform the upgrade. As you can see from the output, Brew installs all software under User Local Seller by default. That location can be changed, but according to the FAQ on the website, I would recommend sticking with the defaults. In my own experience, the default setting has been sufficient for my needs, so I don't anticipate that presenting any problems for you. If I would rather upgrade every software package that Brew manages instead of specifying each one individually, I can just use the upgrade argument by itself. Be advised that this process might take a while to complete. Once that's done, you can always get a full list of the software packages installed by Brew using the list argument. At any time, we can get a full list of the software packages installed by Brew by using the list argument. I can see from the output of brew list that I have an application called SQLite. Here I'll uninstall SQLite using the brew uninstall command. If you ever suspect that something is out of whack with brew, or you're having trouble installing a package, it's always nice to call the doctor. It's a good thing that I just ran this command because it informed me of several problems with my system and was nice enough to tell me the commands necessary to fix those issues. As the output from the brew doctor indicated, I can use the following to determine any missing dependencies. After running that command, it shows exactly why I need to install the xz package, because the Silver Searcher package needs it. All of the brew commands covered so far are great, but my general workflow is far simpler. I usually just want to find the software I need, install it and try it out, and then remove it if I feel it isn't helpful or necessary. So let's search for a package. In this example, I'm going to search for SQL in an effort to find a relational database package. As you can see, it returns a wide array of database packages for me to choose from. Since I previously removed SQLite, I'm going to add it back by using brew install. As usual, the output shows the progress of the installation. Before we install any software from source, we'll need to have a basic understanding of how to work with compressed or archived files. To create files with a .zip extension, we need to use the zip utility, which is capable of packaging and compressing files. Viewing the contents of our documents directory, we can see that we have a few files to work with. Let's compress them using zip to see it in action, but let's specify laptop as the archive name. As you can see, the files were compressed using the archive name we specified, but a .zip extension was added as the file suffix. In contrast to zip, we have the unzip utility, which gives us the ability to list, test, and extract compressed files in a zip archive format. By specifying the L option, we can simply list the contents of the archive created previously. Instead of simply listing the contents of the zip archive, we can also extract the files. We can also explicitly specify a target directory to which the zip file should be extracted using the D option. Here we've told the unzip utility to extract or inflate the files to the temp directory. As an alternative to using the zip and unzip utilities, you can always use gzip and gunzip, which are based upon the limple-ziv algorithm. Let's take a look at an example by looking at the contents of the downloads directory. Here I've downloaded a tar archive for the TCL language. Let's first compress it using gzip. As you can see, due to using the gzip utility, the file size has shrunk down significantly. Using the file command, we also confirmed what type of file it is, gzipped compressed data. Since the TCL file is already compressed, let's show an example using gunzip to uncompress it. The end result is a much larger file, but one that is still compressed using an altogether different format called tar. Let's verify that using the file command. The tar utility has been around for several decades and was originally used to write data to devices for tape backup purposes. But today it is still used for packaging files into one larger file for distribution or archiving. First, let's simply list the contents of the tar archive without extracting any files. The man pages specify that the T option is used to list archive contents to standard out, while the F option is used to specify the file name of the archive to be read. To the astute observer, you might have noticed that flags normally require a preceding character represented by a hyphen. However, for compatibility reasons, the tar command supports what's known as the bundled arguments format. In other words, the dash is completely optional. Now that I know the contents of the tar archive, or tar file, I've decided to extract the contents of it. The X flag is used to extract the archive file to disk, while the V flag is used to display the output in verbose format, which basically lists the files as they're being extracted. As before in the previous command, the F option is used to specify the archive file name to be used during the extraction. Let's now take a look at how tar archives are created. First, we'll create a couple of small files just to show a quick example. And then we'll take a look to verify the contents of those files. Then we can use tar to create the archive. First, you'll notice the C flag is passed, which is used to create a new archive containing the specified items. And then we specify the names of the files or directories that we want to include in the archive. Finally, we redirect the output to a file called numbers. Let's verify the file's type by using the file command. We can see that it is indeed a tar archive file. However, we didn't follow the convention of specifying the .tar file suffix when we created the archive, so it wasn't easy for us to tell what type of file it was without using the file command. Instead, I'd rather follow the convention to make it easier on myself and others who view this file later on. So let's first clean up our mess by removing the original file and recreate it using the convention. If I wanted to gzip the contents of a tar file, I could easily do that after creating the archive. But sometimes it would be nice to create that format in one shot. Let's do that, but this time we're going to create the archive using the Z flag, which tells tar to compress the file in gzip format after creating the tar archive. Verifying the contents of the file, we can see that it is compressed using gzip, but there's no evidence of this file being a tar archive. To do that, we need to uncompress it first using gunzip. And as you can see, the resulting file contains only a .tar file suffix and is in the expected format. As a side note, occasionally you'll come across files that have a .tgz suffix, which is essentially a shorthand format of specifying .tar.gz. Just remember, compressed archive files can be created just the same as before using this alternative. As before, it's a gzip compressed file. We can uncompress it just as before and verify its contents. Just as you can create gzipped tar archive files using one command, you can also extract them in one shot. Let's create that archive first. This time, let's extract it using the same flags as before, except we'll also specify the Z flag so that we can skip the separate step using gunzip. As before, keep in mind that the alternative .tgz file format works exactly the same way. On occasion, you might come across files with a .z suffix. This type of file is created using adaptive limplziv coding. This file format isn't as common as the others previously shown, but I'd like to show you the basics to help you get started. Taking a look at a sample file created in Markdown format, we see the file size is 3031 bytes. To compress the file, simply use the compress command and specify the file names you want compressed. This creates a file of the same name, but with a .z suffix. Also notice the file size shrunk down significantly. Alternatively, we can use the uncompress command to reverse the process and leave us with the original file. To wrap up this chapter, we're going to briefly cover installing software from source. Using the download from earlier for the TCL language, I'm going to change into that directory so we can perform the installation. You'll usually find a README or install file in most common Unix packages, so I encourage you to always read those files first, as they have a lot of details that might be important depending on the type or version of system you have installed. From the installation instructions, it tells me to change into the Unix directory before proceeding with the installation, as there are a number of target platforms supported for the TCL language. The basic approach for installation of most software packages is as follows. This process is not unique to the TCL language. In fact, it's generally the same steps for any Unix package which you'll install from source. So let's break down each step. Running the configure script is usually done to analyze your system and prepare it for selecting various packages to include in the build, as well as other details such as specifying another target installation directory other than the default. Next, we should run the make file. Running the make command is very common in Unix and works by executing commands based on the definition specified in a file called makefile. Those commands essentially build the software in the local directory tree. Once the make command has completed, you essentially have the software built on your system, but it is not installed in the proper location. Before doing that, you'll sometimes see a step called make test, which essentially runs the makefile, but this time runs a series of tests to ensure that the software that you just built is compatible with your system. Sometimes software packages don't offer this step for running make tests, so don't be surprised if it's not available. If the tests all pass, or if you're comfortable with installing the software anyway, you can proceed with the last step, which is make install. However, there's a problem. You'll need to have the proper privileges to install it on your system, so you'll usually need to be logged in as the root user, also known as the super user, or the administrator of the system. Alternatively, you need to prefix the make install command using the sudo command. If all went well, you should have the software installed on your system. Let's try that out by launching the TCL shell. To get the most out of your system, you'll need to have a reasonable understanding of the Unix shell. To that end, it's important to understand that each shell has specific capabilities built in, including commands such as cd, pwd, kill, and many others, as well as certain features that are specific to your current login session, which are commonly referred to as your environment. Within an environment, a user has access to a number of variables that helps them determine the current state of the session, as well as the ability to manipulate that environment. To have a clearer understanding of what an environment is, let's take a look at the current state of it using the env command, which lists all of the environment variables and their settings for the currently logged in user. Common environment variables include shell, user, home, and path. Taking a look at each of these variables, we can see that we're running the bash shell, which is located under bin bash, and the home directory for that user is located under User's Screencast, which is the standard expected location. The last environment variable that I mentioned was the path, which is extremely important. Without it set properly, the shell would be unusable because it determines the directories that should be searched when typing commands, as well as the order in which those directories are searched. As an example, let's take a look at the ls command. As we did in a previous chapter, let's take a look at the location of this command. As you can see, the location is bin ls, but normally we don't type out the full path when running the command. Doing so would be extremely tedious, which shows just how important the path environment variable is to using the shell in a convenient and effective manner. So how does this work? Well, for each command that's typed, the shell will reference the setting of the path environment variable and attempt to find the directory location of the command so that it can be run properly. Let's first take a look at our path environment variable to see the setting. Basically, a series of directories is listed, each of them colon-delimited. So what the shell does is start by searching the user bin directory first. But for the ls command, it doesn't find it there, so it continues to the next directory listed, which is bin. Because the ls command is located there, the shell stops from searching any further and executes the command. However, if we ran a command that wasn't installed under any of those directories listed in our path, we'd get an error because the shell couldn't find the command and run it. Therefore, it's really important that you understand what the path is used for and how to manipulate it to suit your needs. Let's take a look at a small shell script I have under my bin directory. As you can see, it's just a simple script that echoes hello world. But in order to run it, I have to specify the full path. What I'd like to do is just type hello world, just like I do with other commands. But that currently won't work because the home bin directory is currently not located in my path. We can get this to work by changing my path, which can be done using the export command. What I'm doing here is using the export command to specify the variable to be changed, which in this case is the path, then using an equal sign to set it to a new value. That value is a double quoted string which contains the current value of the path, followed by a colon to delimit the path and then the directory that I want appended. It's important to understand that the path variable is expanded within the double quoted string, so you end up with the following setting. As you can see, the bin directory is now located within our path, so we can now run the script using the shorthand version. As a side note, bear in mind that the $sign is used to specify to the shell that you want the value of the path variable and not the word path. As you just saw with the echo command, you can inspect the current value of an environment variable easily. Let's take another look at those common environment variables discussed earlier, this time viewing them each individually using echo. Setting environment variables from within the shell is great when you need to do a one-off or just need that variable set until you log out or exit the session. However, once you do that, those variables that you manually exported will be lost since they aren't a permanent part of your shell's environment. To make environment variable changes persist to the next session, we'll need to set them in an initialization file that gets run each time we log in. Under the bash shell, this usually means setting environment variables within either the .bashrc or .bash profile files. On most Unix systems running the bash shell, there are a number of files that can be executed for each user, including the etc/bashrc, etc/bash profile, and also the corresponding files under your home directory. And the files that are run depend on whether you're running from a login or non-login shell. To complicate matters, the Max terminal handles this a little differently, which by default runs a login shell and in turn executes the .bash profile under your home directory. Let me share a tip that will simplify your setup in such a way where it works properly regardless of how you log in. First, create a .bash profile under your home directory with the following contents. What this file does is look for a .bashrc under your home directory, and if it exists, it sources its contents, which means it reads the file and executes the commands within the shell. Once this is done, all you need to do is configure your system from this file, setting up your aliases, exporting your environment variables such as your path, and many other things that are specific to your account. As a side note, I would only edit the bash-related files that are located under the etc directory when I wanted the environment to be changed for all accounts, as this is a system-wide change. As we saw previously, we can execute files by sourcing their contents, which is normally done with the source command. As an alternative, you can also use the dot command to handle the sourcing. In this example, I'm going to add an alias for changing into my documents directory. So let's first take a look to see how my bash initialization files are currently set up. We can see that my bash profile does nothing more than execute the contents of my bashrc, which itself contains only one alias for navigating up a directory. Let's now set up an alias called docs and append it to our bashrc. And then let's take a look at that file. You can see the alias exists, so let's try it out. Unfortunately, that didn't work, so what happened? At this point, the shell doesn't have any knowledge of this alias since we only edited the file. So let's make sure the alias is set by sourcing the file. As you can see, I used the shortcut approach to sourcing, but you could have just as easily done this. Now let's try out the alias again. And now let's verify which directory we're currently in. Since we sourced it, the shell had the alias variable and was able to execute it. Keep in mind that in addition to shell initialization files, there are other applications on the system that use dot files, such as vim, tmux, irb, and many others. So anytime you make a change to those files, you need to source them before those changes will take effect. However, if I wanted to undo my work here, I could always unset the alias by using the unalias command followed by the alias itself. Here's an example. Now let's try it out to see if it still works. As intended, the docs alias was unset. On a final note, keep in mind that you can always find a list of aliases for your current environment by using the alias command.